Hello everyone, welcome back to another video for the series. I'm Inoq and today we'll be solving 2026 EGMO problem number 4. Um, I am not sure, but I don't think I ever introduced EGMO or European Girls Math Olympiad in the series before, so very excited to share this problem. And for some reason, I think it is because this exam was held this year, but I wasn't able to find solution to this exam yet in the internet. So I'll be sharing my personal solution that I found while solving this problem. And if you see any error or if you think there is a problem with my solution, please feel free to leave them in the comment below. I'll be sure to fix it. And without further ado, let's get started. Let an infinite sequence of this satisfy that and that for all possible n. Show that the following inequality holds for r equals 2026 to the power of 2026. After reading this problem, the very first thing that I tried is just ignoring this problem and ignoring the last sentence and trying to prove that it holds for all n, because I think the reason why they had r equals 2026 to the power of 2026 is because it was in the year 2026 and they didn't want the students to just brute force it and solve it. I think, not sure. So I was pretty sure before starting that this inequality holds for all n. And actually, before doing that, we have to find patterns. So I tried a sub 1 equals a sub 1, a sub 2 equals a sub 4 plus a sub 5, a sub 3 equals a sub 6 plus a sub 7. Not sure why I wrote that here. Oh, where's the eraser? It's a sub 2 plus a sub 3. Now, and this is 1. And when we substitute a sub 4 plus 5, 6, 7 equals 1. And naturally, when you continue, I tried until a sub 5 and found a pattern that a sub n plus all the way until a sub 2n minus 1 equals 1. So this is what I found with the pattern, but we have to actually prove it. We have to prove that it is true. So let's write a lemma. That's lemma plus a sub 2m minus 1 equals 1. Now, I forgot the word. Is it proof by diagram? I forgot the word, but actually instead of proving rigorously, I want to show a diagram or a tree that goes like this. So we have a sub 1 here. A sub 1 is the sum of a sub 2 and a sub 3. A sub 2 is the sum of a sub 4 and a sub 5. This is the sum of a sub 6 and a sub 7. A sub 8, 9, 10, 11, 12, 13, 14, 15. So what I want to show here is let's say n equals 4 in this case. Then we will be adding a sub 4, 5, 6, 7. Now, adding this row is the same as adding a sub 2 and a sub 3. So the sum of this third row is the same as the sum of the numbers in the second row. And the sum of the second row is a sub 1, which is 1. Okay, so just by looking at this pattern, it goes on forever, obviously. we notice that this lemma holds for 2 to the power of n or k, because starting from here, a sub 8, it will end at a sub 15, and by induction or inductive hypothesis, we can show that the sum of every row is equal to 1. So we know that the sum of the numbers in every row is equal to 1. Now, what if n is not a power of 4? I mean power of 2. In this case, we can divide the number into odd or even number, and let's go with even first because I think it's more intuitive. Let's try and see a sub 6. Where is a sub 12? It's right here. So this is very important that this holds for every a sub n, that a sub 2n would be right above a sub n, and the left node. It will be in the next row and the left node of a sub n. In other words, a sub 6 plus 7 plus all through 11 will be this plus until here. And what is the sum of all numbers in, let's say this is nth row, because we want to generalize. What is the sum of all numbers in the n plus 1th row, but before let's say that this is kth row. What is the sum of all numbers in k plus 1th row, but before a sub 2n? That will be every number. So as you can see here, it will be every number in the kth row before a sub n. In other words, if you want to add a sub 6 plus a sub 7 plus all the way onto a sub 11, that will be the same as adding a sub 6 plus 7, 4, and 5. That is the sum of all numbers in the kth row. In other words, if we start from an arbitrary even number, we will get the sum 1, because we will be adding all the numbers in the kth row. How about when we try even odd number? Let's say a sub 7. Now, where is a sub 2n in this case? It will be in k plus 1th row, and it will be the second node of a sub n minus 1, which is right here. So if you want to do a sub n plus 1, 2n plus 1, a sub 2n plus 1, which is an odd number, it will be the same as adding all the numbers just before the first node of a sub 2n plus 1. And that is, as you can see, all the numbers before a sub 2n plus 1 in the kth row. In other words, a sub 7 or any arbitrary numbers to a sub 4n minus 4n plus 1 will be the same as adding all the numbers in the kth row, which is equal to 1. Therefore, our lemma holds. I know I didn't write it very rigorously, but I think this idea is correct, and this should be correct. If you think there is a more rigorous way of writing it, please feel free to share in the comment below. Okay, now that we have this lemma, we can prove our left inequality, which is this one. So let's prove this. We know that by this lemma, we know that the greatest possible number, the least possible number, so mean of this occurs if and only if all the numbers are equal, because of this condition. In other words, the minimum for a sub n is equal to 1 over the number of terms here, and we have n terms, so the minimum of a sub n equals 1 over n. In other words, a sub n is greater than or equal to 1 over n. So we proved our left hand side, anytime I don't like this explanation actually. For the sake of contradiction, I think that's better. Of contradiction, let a sub n is greater than 1 over n. Then oops, sorry, I flipped it. Yeah, less than n. Then a sub n to n minus 1 will be less than 1 over n, and the sum of all numbers from n to 2n minus 1 would be less than 1 over n times n minus 1, which is less than 1. This is not equal to 1, so this is not true. So by contradiction, we know that 1 over n is less than or equal to a sub n. Now let's prove our right hand side, which is a sub n is less than or equal to 2 over n plus 1. Okay, so this part is actually also straightforward. Let's take a look at this. To prove this, we first want to prove that a sub 2n minus 1 is always less than or equal to 1 over n. So how do we prove that? It's the same as before. For the sake of contradiction, let a sub this is greater than 1 over n. Then, by definition, we know that our sum k equals n to 2n minus 1 would be greater than 1 over n. Hold on, sorry. Oh my gosh. Good thing that I didn't have anything there. Times n is equal to 1. So this doesn't hold for sure. Yeah, it's equal to 1. So we know that if this is true, then our sum will be greater than 1, which is not true. So we know that this is true. Let's continue. So we know that a sub 2n minus 1 is less than or equal to 1 over n. Okay, what is 1 over n? This is equal to 2 over 2n minus 1 plus 1. So for odd n, a sub n is less than or equal to n plus 1 over 2. So this is true. Okay, I will be honest here. I was actually quite stuck from now because we only need to prove that this works for all even n, and the same method that we use here doesn't quite work because a sub 2n minus 1 could be less than 1 over n, and we cannot prove this inequality. So I spent most of my time solving this problem here because I was stuck here, but there actually is a very simple way to continue from here. And that is because we know that this is true, yes, actually, we can continue from our definition. Sorry about that. We know that by definition this is true, as shown here. So, and this thing is less than or equal to 1 over n. So this is less than or equal to 1 over n, and a sub 2n minus 2 is less than or equal to 1 over n. And this implies that, let's substitute n plus 1 here. A sub n, substituting n plus 1, we get a sub 2n is less than or equal to n plus 1, or 1 over n plus 1. Okay, so we are done here because a sub n equals a sub 2n plus a sub n plus 1 by definition, and because a sub 2n plus 1 also a sub 2n plus 1 is less than or equal to oh no, it's right, it is right. Okay. So because we just proved that this holds for odd numbers, we know that this is true. In other words, a sub 2n plus a sub 2n plus 1 is less than or equal to n over 1 over n over n plus 1 plus 1 over n plus 1, which is equal to 2 over n. And this is the same as a sub n is less than or equal to 2 over n plus 1. And that proves our right hand side. So we just proved that our left hand side is true for all n, and our right hand side is true for all n. Therefore, this inequality holds for r equals 2026 to the power of 2026. I was actually, I think this problem was really interesting and also very meaningful because it looks very simple at first, and it is actually when we just prove this lemma, then it becomes simple. But it's one of the Olympiad problems that so I solved lots of Olympiad problems, but it's one of the problems that I can finish without external help, and I think it was a very fun problem to solve and share with everyone. If you like this problem and if you think other people will enjoy this problem, please don't forget to like this video and share it with everyone. And also please don't forget to subscribe. Thank you so much for watching this video, and see you in the next video. Bye.